that in my last slide. So what really is failure analysis? Failure analysis is nothing but we analyze the failure after it happens. So supposing a component has failed, so we go back to the application, we go back to the field, have the field visit, get the data, get the component back, analyze it. So it is all kind of post-mortem that we do on the failed part. But do you really think this will be useful if it remains at that stage? Not at all. Because the inputs that you get from a good failure analysis, unless close them back or close the loop with your product or with your application or with your process, it is of no great use. So failure analysis is a very, very vital step in our endeavor in the industry to have a right first time product or the predictable execution. You must have heard this word, predictable execution. So the predictable execution cannot happen unless we act on the feedback that is obtained from a good failure analysis. So this is a principle. So no matter how much how great we do our FEA, no matter how great we do our FMEA, no matter how great we do all the plugging of loopholes in our processes, unless you put your product in the field and unless it runs in the field, there will be one or two failure modes that definitely will be different than what you thought of initially. So that is why this failure analysis is very important, because in real life you cannot arrest all the failure modes right at the launch of the product or right at the beginning. You are say 90% there, but 10% inputs have to go from the field failures, and that is where it forms a very critical part. Okay, so I think with that we'll move ahead. Please let me know if I'm really not audible or anything. Let me know, ping me or interrupt me and tell me. Otherwise, I'll just continue because for me there is no chance to know whether I'm audible properly or not. Okay, so this is the roadmap formed for today's presentation. As you can see on your screen, so I'll be touching upon the metal failures mainly, the types of metal failures. Then there is a category called fatigue. So types of fatigue failures. Then friction and wear, they are hand in hand. So types of wear failures. And then I will also touch upon in brief the basic tools for failure analysis. What one needs for failure analysis. And as Sandeep has indicated, so I request everyone to be quite, be agile, because there is a quiz at the end of the session, and if you really, pay your attention, the answers are there in the presentation. So you can very well, you can really fare well in those quiz, in those questions. And finally, I will end up with a takeaway that I indicated on the first slide. So this is what has been planned today. So let us go one by one. Okay. So, as you know, there are two prominent failures, ductile and brittle. So, what really is a ductile fracture? Before I go into this, details of individual failures, let me tell you very honestly that Sandeep indicated that I will be presenting some case studies. So, I am not going to per se present any case study from any industry. So, I maintain that confidentiality and I maintain that IP related things. But I have taken the photographs from the common domain, common public domain that is available. So, I have ensured that I'm not disclosing any details for any of the companies that I have been through. So, I have made it quite, informative, and the information is available in the public domain. So just a clarification on that. But I do have a plan to have one more presentation done like this for an extended period that will deal upon the case studies, masking all the information so that we maintain the confidentiality. So that is in plan. So I'll be coming up with that shortly. Okay. So coming to ductile fracture, metal can fail in two manners, ductile and brittle. So what is ductile fracture? As you can see in the photograph, the typical ductile fracture of steel is shown here. So, this is how we experience the fracture when we do tensile test of material. So, just a moment. Yeah. So, as you can see, the fracture is characterized by tearing of metal accompanied by gross plastic deformation. So, there is a significant plastic deformation before the part fails. And a typical fracture appearance in the ductile fracture is gray and fibrous. So, what could be the reasons for ductile failures? So, as some of them have been listed here, that it's basically the overload conditions that get created by the service abuse, defective processing, say faulty treatment, or defecting the material, defective material. So, these are typically the reasons why the material fail.
Mahesh, your screen has gone.
Oh, is it okay now?
No, not yet.
I am also not seeing my camera. I cannot do anything. Just a moment.
Now try again.
Yeah.
Yeah, it has started to come.
I think some technical goof up.
Something happened. Okay. Yeah, continue. We can now see it.
Okay. So this is how the brittle material will fail in brittle manner. So you can see the fracture shown here. It is characterized by low or no plastic deformation. There will be no indication before failure, and typically the appearance will be bright and granular. So looking at the fracture, you can differentiate whether it has gone in ductile mode or brittle mode. So these are some quick checks that one can see on the part. So it can be, what are the reasons? It can be initial defects like cracks, folds, laps, inclusions, laminations, or there can be stress resistors like notches, sharp fillets, threads, splines, keyways, uh, cracks resulting from machining also or heat treatment, fatigue, hydrogen embrittlement. That is also one very interesting thing happening in industry. Residual stresses, the prior residual stresses present in the material. So there can be n reasons. Some of them are documented here. So basically, this is very fundamental. Like ductile materials, they have extensive plastic deformation prior to failure. So a lot of energy is absorbed. That is toughness before fracture. You can see this engineering stress in diagram shown for a ductile and brittle material. Whereas brittle material will fail, without any indication, with very little or no plastic deformation, and the toughness will be very low. What exactly or how exactly this failure takes place? So these are the three cases that are shown here. One is for very soft material like lead or gold at room temperature, or if you talk about polymers and glasses at high temperature. So figure A, what you are seeing here is like there is a very thin necking that can happen, that will happen before failure. So it's a quite ductile material. Mostly whatever industrial steels that we have or industrial materials we have, they are moderately ductile fracture, and one shown in B, typically they will fail in the manner shown in B. And brittle fracture, no indication, no plastic deformation, is C shows that no mechanism of failure.
Mahesh,
So
could you be a little
typically,
bit louder, please? Very loud. Your
yeah,
sound is very low. Yeah.
okay.
Thank you.
Is it okay now?
Yes,
Is
yes.
it
This is
okay?
okay. Yes, yes,
Okay.
yes.
Okay. So the C category is for the metals that are at sub-zero temperature or ceramics because they are brittle in air is brittle. So they will fail without any indication. What exactly is the mechanism when material fails through ductile mode? As you can see, there are 5 stages shown here. First, it will start to nake. So the second, there will be cavity generation, uh, which is nothing but the microvoids that are present in the material that is dislocation. They will start, forming cavities. Then the cavity will coalesce. It is called cavity coalescence, and they will coalesce to form opening or void. Bigger void is called crack, and then this crack will propagate, and finally it will rupture by shear, say about 45 degree to the load axis, loading direction. So this is how a ductile material will fail. These are typical 5 stages that you can see typically in ductile material. So this is the cup and cone fracture shown in aluminum. So typically these are the two counterparts that normally you observe when you break it in tensile. And scanning electron microscopy photographs are shown here just to indicate. So it is typically dimpled ductile, what term we use. So these dimples are nothing but the microcavities that actually initiate crack formation. So exactly opposite is brittle fracture. So as I told, the crack propagation is very fast and it propagates perpendicular direction of applied stress. And it is typically called a cleavage failure, where it is a breaking of atomic bonds along specific crystallographic planes. That is how the metallurgical mechanism that happens in brittle failure. And there is no appreciable plastic deformation. So you can see the fracture shown here. You can see it's quite plain, quite planar. It's not like the ductile one, which has say 45 degrees shear stress axis. So these are very, very quick points to judge whether the material has gone by ductile failure or brittle failure. And in brittle failure, it can go in two manners. One is called transgranular, the other is called intergranular. So transgranular is nothing but rupturing of grains, and the crack will travel by rupturing the grains. So, and intergranular, the crack will follow the grain boundaries, where normally those are weakened due to some embrittlement or impurity. So typically happens in embrittled failures, embrittlement failures. So you can see here the difference in the fracture as shown in scanning electron microscopy. So this is typically intergranular failure is typically called as honeycomb. You can see like cellular structure. So it's quite clear if the crack. And majority failures normally are intergranular failure in brittle that we observe in the industry because of some embrittlement or some impurities on the inboard. So now coming to fatigue failure. So basically fatigue happens under fluctuating and cyclic stresses. And as a matter of fact, the failure actually can occur at very low loads than under the static load. So if you keep it loading in the static versus the part is rotating, so it can fail at a very low load. That's called fatigue than what is expected. So in the industry, 90% of all failures of metallic structures are fatigue failures. That is how the data says. So mainly, the failures that we observed in GS and all the industrial applications, aircraft, machining components, etc. So that is the reason is fatigue failure. The root cause could be various, but the reason is fatigue. So what are cyclic stress is what is important in fatigue. So you can see on the screen some acronyms or some symbols. So what are the main terminologies used in fatigue? Nothing but mean stress, range of stress, stress amplitude, stress ratio. You can see it's a sinusoidal wave. So tensile stresses are positive and compressive stresses are negative. So it's a sinusoidal wave, and several such waves form the alternating stresses where a component is subjected. So this is mainly used in fatigue life calculations. The determining fatigue life of metal. So these are the terms that are important in that. How basically a fatigue life of a material is established or estimated. It is called a rotating bending fatigue test. As you can see here, there is a dog bone shaped sample made out of the part, and it is flexed by holding it as shown in the figure, and under load, under bending load, it is actually rotated. So you can see the counter here, which actually counts the number of cycles the part is going through prior to failure or breakage. The aim is to break the sample and record how many cycles it has taken to break. So, what's the use of this? So, with this, at different loads, when we conduct this test, we get a stress versus number of cycles graph for the part. I'll come to that in a minute. So, there are two categories: low cycle fatigue and high cycle fatigue. So, typically, low cycle fatigue happens under very high loads when you subject the component to very high load, so it fails in like very early. It fails very early or in low. Number of cycles are less. And high cycle fatigue is the loads are not that high. It's basically a low load failure, but the number of cycles are large. So these are the common terminologies we will see in industry that we use. It's a low cycle fatigue or high cycle. So this is what I was talking about, generating SN curves. So SN curve is basically nothing but stress versus number of cycles plotted for individual material. So what is fatigue limit? Fatigue limit is nothing but the flattened portion you see in the curve is called the fatigue limit of the part or of the material. So if you subject the material to a stress below fatigue limit, it will never fail. That is how it indicates, or it will enjoy the durability, long durability, and will never fail. That is how we get guidance. What are the loads the part can be designed to. Now coming to the actual fatigue failed samples, you can see here a bending fatigue failure in crankshaft shown here. So you see this piece, the fracture. This is a fracture. This has gone through pin, crank pin, fillet, and you can see this fatigue striations here. And so 3 stages. It happens in 3 stages. Fatigue is characterized by 3 stages. So you can see crack initiation that has happened through pin fillet here, and then progressive cyclic growth of crack, which is the beach marks that you are seeing here, and the sudden breakage, which is called the final fracture. Hope I am audible to the audience.
Bit louder, please.
Okay.
Mahesh, if you could be louder, yeah.
Okay, just
Because there are a lot of people talking about,
okay.
Yeah. Also, to the participants, I would request next time onwards, please put your headphones on. So that will be, we will not miss out any little of sound. I mean,
Okay.
little of even the words of the speaker.
Yeah.
So that will be also better, because these days sometimes the net quality is not that good. Because I can hear him with this headphone on. I can hear him very well. But
Okay.
of course, if that is the issue, then please, I would request all the participants to use that one. And yeah, thank
Okay.
you, Mahesh. Go ahead.
Yeah. Am I okay now? Audible better now? Hello? Hello? Hello?
Yeah, speak a little, speak for some time. I will give you a feedback.
Okay, okay. Yeah, no problem. So as you can see in this slide, the fatigue basically happens in 3 stages. The first is crack initiation, then progressive crack growth, due to cyclic stresses, and then final sudden rupture of remaining cross section. So as you can see here in this crankshaft piece, the crack initiation happened through pin fillet, and then these are the beach marks, and the final rupture zone is seen here. So typically 3 stages of failure. There are certain types, fatigue types depicted here. So it can be unidirectional bending fatigue. In unidirectional bending fatigue, the crack forms from one end or one side. Say suppose it's a diametrical round part, then it will form from start from one end and go to the other end, and it can be through single origin or it can be through multiple origins. It depends on the stress concentration in the jaw. There can be geometric features that add to stress concentration, but depending on moderate to severe or low to severe stress concentration, the number of origins can change. It can be single point or multiple points. The second picture shows the torsional fatigue. Again, torsional fatigue starts, you can see the twisting of the fracture lines here, and starts from the periphery, and you can see the final fracture is little off center. So when I'll talk of rotating bending fatigue failure, you can see in the ASM handbook also they talk about similarity between torsional fatigue and RBF. So I will touch upon that. So you can see here the twisting of the lines, and this final fracture zone is little off.
Mahesh, request you to share your screen again. We had another breakdown.
Is it okay now?
Yes, we can now hear you
Okay.
and see the presentation also.
Sure.
Make it full screen, please.
Yeah. Yeah. Is it okay now? Can I
Yes,
proceed?
yes.
Okay. Yeah. So now this is what I was talking about, rotating bending fatigue. As you can see in this picture, the cracks starts from multiple origins on the periphery and it moves inside. And you can see here the final fracture is right very close to the center. So this is precisely the difference between torsional fatigue and RBF. And of course, there is no twisting of lines, so that is an additional point. But on the if somebody sees superficially, uh, the fractures can get misled because of the appearance similarity in appearances. So RBF is the fracture that starts from periphery from multiple points, and the fracture travels inside towards the center, and the final fracture is close to the center. Now reverse bending. What is reverse bending? Reverse bending typically we see in the bolt failures where the bolts are not sufficiently taut, or even in shafts which are not sufficiently taut. So what exactly happens is, because of the loosening, the fatigue starts from either ends of the diameter, and it moves inside. So as you can see from the picture, the fatigue is starting from multiple origins from both ends, and the final fracture zone is in the center. So this is a very characteristic of feature of reverse bending. Now, so these are the very quick checks when we get to see fractures. At least we, by looking at them, I'll talk about the tools later, but at least the naked eye examination and some low power examination gives us a very good idea as to what must be the fracture mode. Now, this is another type that we observe in engine components, rolling contact fatigue. So, what is rolling contact fatigue? It happens in all the components that are in touch, that are in contact with each other, and they have a motion amongst them. So, it can happen in gears, camshafts, and rolling element bearing rollers. So, typically, what happens? Is that okay, doctor? Any problem? Like inaudibility or anything?
No, it is okay now. Please
Okay,
go ahead.
okay,
Yeah,
thank you.
please go ahead. Yeah.
Yeah, yeah. So the crack typically generates subsurface level, and then it actually travels and connects to the surface, and the portion is plucked off. It is typically called as splitting. We observed in camshafts when camshafts experience overspeeding in engine operation. So, and this is also typically called as butterfly wings. If you see an ASM book, it has been described as the butterfly wings. The pattern of crack is like butterfly wings. So this is rolling contact fatigue that happens in the contacting surfaces. The slide here talks about thermal fatigue, typically observed in pistons of the engines. So uh, you can see in the first picture there are cracks happening on the crown of the piston. So you can see a couple of cracks or 2-3 cracks here. And then the second picture shows the severity or the severe condition of this thermal cracking. Why this happens is because the piston top is subjected to repetitive heating and cooling due to the combustion. So it is subjected to thermal stresses, thermal stresses. So that's why these small the micro cracks generate, and then they eventually lead to failure of the piston. In addition, you can see the valve stamping also on this piston. The reasons are different, but the basic here is there are thermal cracks, so something has gone wrong in terms of the temperature in the engine, combustion temperature. So coming to the causes of fatigue failures. So what could be the causes of fatigue failure? So if you see the causes, they are interlinked. It only the manner in which the part fails that determines the mode of the failure. But if you see for fatigue as well, there can be service overloads that can affect high cycle or low cycle fatigue. Sorry, high stress, low cycle fatigue. Then there can be a bad design where there are abrupt changes in adjoining section in the part. So it's basically a design issue. Or there can be inherent material defects like inclusions, cracks, porosity, shrinkage, manufacturing flaws like sharp radius, improper blending of radius, and residual stresses, tensile residual stresses that can happen in machining operation like grinding and all the polishing, or every machining operation will create some kind of residual stress which we need to mitigate. So these are the typically reason, and I have talked largely in my presentation about the surface fatigue that happens, but there can be a subsurface fatigue generation, and basically these are the causes that can generate subsurface fatigue. Inclusions, crack or porosity or shrinkage, whatever is inherent defect in the material, it will start a subsurface fatigue initiation, which you can see. I don't have the photograph right now with me, but I'll include that. But typically, you can by the way of location of fatigue initiation, where whether it starts from surface or subsurface, you can go ahead about your analysis, because that will change the direction of analysis. Now coming to the wear failures. So wear and friction are hand in hand. So whenever there are surfaces in contact, there will be a friction, and if they are under load, there will be definitely, if they are under load and in motion, so definitely the wear will result. So that's why wear is defined as progressive loss of material from a surface as a result of relative motion at the surface. Now wear is actually a gradual process, and there are no accurate means to quantify it. So as I told, friction and wears, they are influential on each other. So it's really a complex relationship, and there are many factors that need to be studied to arrive at a proper root cause. Screen is not changing. I'm just trying. Yeah. So why do we focus on wear in industry? Because wear is undesirable. Because there can be increased clearances between moving components, loss of precision, and because of that there will be increased vibration and loading. So actually it leads to significant maintenance and replacement cost in many applications. So, and the efficiency also is reduced of the equipment. So that's why wear is undesirable. Now coming to different types of wear. So there are few types have been listed, or there can be further, but these are the main types that we observe in industry. You can see on your screen: adhesive wear, abrasive wear, fatigue wear, erosive wear, corrosive wear. So as mentioned here, many situations will have multiple wears types of wear operating simultaneously. So here the adhesive wear mechanism is shown. Whenever two contacting surfaces are sliding against each other under load. So as you know, there will be asperities, which are high points in the contacting materials. So these high points will collide with each other while they are moving against each other under load. So what happens? This collision will result in adhesion of the high points, and there will be a chipped off material or the plucked material from one material to other, depends on the which hardness is more. So this material will be firmly glued to the hardened material. So this is called adhesion or the adhesive wear. It can be mild or severe depending on the pressure and velocity. These are the two very important parameters in friction: pressure and velocity, called PV factor. Uh, so depends on that. The adhesive wear can be mild or severe. So mild wear will have low material removal rate, and then the debris will consist very fine oxidized particle, and surface will look like smooth. But severe wear, there will be high material removal rate, and debris will consist of large metallic particles or flakes, and surface thus becomes very rough. So this is typically shown in a roller, camshaft roller or roller that gets engaged with camshaft. So this is the adhesive wear, and you can see the severity here. This is a scanning microscope image. So you can see this, all the deposited or the glued material here. So what are typically the cases where you can find adhesive wear? As I told, that two surfaces need to slide against each other under pressure, under load, and under load. So the examples are chalk on a blackboard. This is a very common example that we see. A sliding door on its track. Then our body, if you talk about our body, it is bone against bone, such as the hip joint. Then shears and guides in metal rolling mills, and levers in gearboxes. So wherever there are sliding surfaces, adhesion can happen. Adhesive wear can happen. Now coming to the second wear, which is called abrasive wear. Abrasive wear happens mainly because of the dirt particles that gets contaminated into the contacting surfaces. So basically, the way to reduce abrasive wear is to increase the hardness and decreasing the roughness of the material, and also flushing out all the contamination, that is dust, dirt, and abrasive particle from the system. So otherwise, abrasive wear will happen. So basically, abrasive wear is because of the particle that gouges or impacts a surface. So it can be two body or three body. Two body, what is two body? So digger blade that hits gravel embedded. So in the earth moving equipment, if the blade is digging the earth, so it can hit a gravel embedded in earth, and there can be an abrasion happening. Circular saw, when it cuts, there can be abrasion, or any cutting or polishing tools. When they are cutting, abrasion can happen. Three body, what is mean by three body is any grit particles that could get caught between two surfaces. For example, lube oil. If lube oil has a contamination, then it will wear out the contacting surfaces. Then you can see polymer extrusion dies, they wear due to filler particles in polymer itself. So they come out and they form a third body that wears, grit blast and all that. So basically it's a two body or three body wear. Here it is shown schematically. So this is typically how the abrasive wear will look like. So uh, you can see that pure abrasive wear, there will be no tearing of surface, as you can see in adhesive. Abrasive will have a scoring marks like this, what is shown in the picture. Now, this is another interesting wear type, which is called as erosive wear. So, what exactly happens? Classic example I will give in the cylinder liners in the diesel engine, where the water cooling that is used for the liner, actually there is an aeration that happens around in that water cooling jacket, and actually the water forms a very tiny bubbles. Water bubbles are formed and they implode on the liner uh, outside diameter, and they pluck out the material. So what is that is called, typically called as cavitation erosion. So here you can see the that in the case that I mentioned, it was water bubble, but there can be external impact on the surface by a particle, and then it will chip out the material. This is typically called erosion. It will erode out the material. So the typical case I describe is cavitation erosion that we see in cylinder liners. So this is how even if when we do sandblasting for the removal of dirt and these stuck parts from the steel, this is the same mechanism that we employ. It is sand part. We blast it by sand particle, and it removes that stuck debris or the contamination. Now, what is contact fatigue? I described rolling contact fatigue. So here again the same schematic is shown, that the contacting or rolling. This is a static contact. That the rolling contact. In the rolling contact, you saw the subsurface generation of crack. So here you can see subsurface generation of crack, and then it actually extends, and this entire piece is removed finally. So basically it happens under stress. These cracks starts generating at subsurface level, and then they propagate and extend up to surface, and the whole thing is chipped off, which is normally called as pitting. And very prominent failure of this sort is observed in camshafts, where the camshafts under high speed or overspeeding, they chip off, or they have the pitting defect when they experience overspeeding. They fail by pitting, which is nothing but rolling contact pitting. The same thing is depicted here. It is called as fatigue wear. So this is an engine lifter. It is an engine lifter, which is nothing but what I was talking about, cam follower roller or cam follower element. So this is how the cracks will generate in the subsurface level, and they will connect to the surface and remove the whole chunk over extended operation. Now there is another variety called as corrosive wear. We saw erosive wear. There is a corrosive wear. So if the part is in contact in the acidic environment, say like sulfuric acid or very highly corrosive environment, so the corrosion film will form on the part, and so this is a part strata and the substrate, and then this corrosion film will grow, and actually it will remove that material from there, and the material will be formed. This is called as corrosive wear. Now fretting wear, what is fretting wear? The parts are in contact, they are in motion, and there is a relative motion in the part. So they are continuously hitting against each other because of the relative motion. So fretting is so if you see the surface, you can see the micro welding on the surface, which is very tiny. The high spots in both the material will they will glue, so they will form a sticky substance on the surface, which is called as micro welding of asperities. So you will see a very damaged kind of or indented surface when you see a fretting there. So that is a sign that there was a relative motion on the part. It can happen in static contact also, because in static contact, if there is a slight relative motion, then the fretting wear can be seen. Now, what are the temperature-induced failures? Low temperature failure, high temperature failure, and I discussed already about thermal cracks. So, low temperature failure is nothing but sub-zero temperature failures. Typical case we can date back is Titan, where the Titanic ship was going through like going. It was hit by an iceberg, and since it was the temperatures were freezing, the metal lost its toughness, and that's why the iceberg hit it, and there was a crack generation, and the whole ship sank. So what really happens is the material loses its ductility at a very low temperature, like sub-zero, and even the ductile material behaves in a brittle manner. So that is how it can have a catastrophic failure when it is subjected to a very low temperature, like sub-zero temperature. Then high temperature failure also can happen, because if they are subjected to high temperature and constant load, they undergo a mode of failure which is called trip, which is irreversible deformation. So there will be a permanent deformation, and material will lose its intent or ability or the use. Then thermal cracks are already discussed due to cyclic heating and cooling. The material will form micro cracks, and that will lead to failure. Okay, so coming to the what are now the tools that we can use for failure analysis. So I will also touch upon the SOP for failure analysis once I discuss these tools. So what needs to be done for proper failure analysis? So as you can see on your screen, uh, it starts actually with visual observation. So we have to observe the part before even initiating any kind of processing on that, like cutting or even taking hardness or whatever. So first thing is visual examination, and then capturing the observation through a photography camera. That is the very first step that one needs to do. Then, if needed, or that is always required, that you take it to a low power lens or a stereoscope, where you can have further more observations on the part, like how it has failed. I have described the failed samples, few failed samples in my presentation. So what kind of characteristics that we see on the failure or on the fracture? So those can be ascertained by low power lens observation or stereoscope observation. And then you can go with the NDT, non-destructive testing, which is basically see the NPI crack testing, whether the crack part has additional cracks, or can you see some additional cracks besides what you are seeing as failure or the failed part. So are there any indications that it has been subjected to overstress or anything that you can ascertain, which is called as magnetic particle inspection. You can also have entities like radiography or ultrasonic testing, AD current testing. So these are the tests meant to be done before even taking the part for destructive testing, because destructive testing is the last step that one needs to do in terms of analyzing the part. So and then certain things will also need a very high-end kind of analysis, which is called a scanning electron microscope analysis. So in stereoscopic observation, if I see that there is a subsurface fatigue in the part, and I do suspect that there is a non-metallic inclusion that has led to this failure. So I need to then have a tool to ascertain what kind of non-metallic inclusion is that. And for that I need to go to scanning electron microscope, where I can see that under very high magnification, say a couple of thousands times. And then I can also use mere scanning electron microscope will not suffice my purpose. So I will also need energy dispersive spectrophotometry that will tell me that spot analysis, where I can do an X-ray analysis, and it will give me the elements that are present there in that particular region. So whether it is an oxide or it is a kind of, what do I see, whether it is oxygen, calcium, sulfur, whatever I see. So typically a non-metallic inclusion will display these things like calcium, sulfur, oxygen. So I need to take that information. So that actually will confirm me even the source. So not only I am seeing the symptom or I am seeing the root cause there, but I can also ascertain where it has come from. So where in the process it has come from. So this is an excellent tool, scanning electron microscope. So coming to the SOP, standard operating practice for failure analysis. So conventionally, when I'm interacting throughout my career of say now 28 years, I have been observing that there is a general misconception or misinterpretation of failure analysis, that it's a metallurgical analysis essentially. Failure analysis is nothing but metallurgical analysis, which is a very, very grossly wrong conception that people have. Failure analysis is much wider. Metallurgical analysis of failed parts is a part of the entire analysis. So the failure analysis actually starts from where the action has happened, like in the field. So the moment we get to hear that something has failed in the field, actually the process of analysis starts right from there. So one needs to really visit, or the service engineer concerned who is looking after the application has to have certain observations done on the application first, and he has to prepare a first kind of FIR, first investigation report, and he needs to come up with all the observations. What was the observation? Whether there was a heavy noise observed, or there was a loss of pressure observed. If I am talking about say engine operation, so all these things that person needs to document, and he has to actually submit along with the failed part, and not only the failed part but the allied parts. So suppose if I am talking about the crankshaft, I must get to see the roller that is in touch with the crankshaft. If I am talking about crankshaft, I must see the bearings of the crankshaft also, because just looking at the failed crankshaft piece, I can see, I can tell what is the fracture mode, but what is the real root cause, or what must have gone wrong. I will not be able to tell unless I have the complete field information and allied part observation. So first step is preparing that FIR by the sales engineer, or if there is a visit specifically made on the field. The thing here is it has to happen right at the time when the failure has happened, because you will get to see a lot of evidences. If you delay that, then you might lose many of the important facets of the failure. So I like this concept of Japanese concept. Like you have to go to the gemba, which is the workplace, or in this case the location of failure. You have to observe the genbutsu, which is the object or the piece in concern, or the part in concern, or the application in concern, and that has to happen in genjutsu time. So what is genjutsu? Right when it has happened. So it's very important that when we get to know that such and such thing has failed, the people concerned have to immediately visit that place, whosoever is near, and get those things documented or captured or photographed. That's a very vital thing, and in most of the cases we actually don't do a good job in this concern. Actually, we just when the failure happens, the immediate reaction is to just to dismantle and remove the parts, which is not correct, because you have to have proper observation even before touching the application, and then you can go on subsequently dismantling and take proper observations on the failed parts. So number two is have the proper observation on the application, and when you are dismantling, have the proper observation on the allied parts, on the failed parts and allied parts. Capture all the things that you can do with the visual observation and with the photography, camera photography, because this is something that will never be, we will not be able to repeat this if we miss it, because the numbers. Suppose it's a crankshaft failure, so the number one cylinder bearing, number two cylinder bearing, suppose it is a four-cylinder crankshaft or a six-cylinder crankshaft. So identifying those bearings per cylinder is very important. Upper, lower, what were the observations? If that is gone, it is the same way a murder mystery is evaluated, or crime is evaluated. So it starts with the dead body. They capture the all the observations that and the location where it has happened. So if you see those murder mysteries being solved, so they don't turn down any evidence as not useful. They capture all the evidence. That is how we should go about doing a failure analysis. We have to capture all the evidences that we get to see, and the elimination can happen later, because we at the right at the collection point we cannot eliminate any observation that may prove to be a significant observation later. So we have to collect maximum information. So FIR, then the photography of the failed application parts, and then dismantling, identifying the correct manner, and the whole thing. Then you have to get in touch with the technical people to what would they need back for their analysis at the factory end. So if it is a crankshaft, the crankshaft failure may be a effect. It may not be the first cause. Something else has failed. So they will say along with the crankshaft, send us even the piston also, or even the valve also. So whatever they demand, if that comes along with the failed part, that gives a lot of information for the analyst or the expert who is doing the failure analysis. So, in absence of that, it is just a kind of bits and pieces job. So I always tell to my team or to my students or to the people who are in touch with me for helping them out in their failure analysis. I see that together we need to see the elephant. We cannot be like those blind people who just see the elephant in bits and pieces. Somebody says it is a pillar, somebody says it is a rope. So together we have to see that elephant, so that we get maximum information. So it's kind of a jigsaw puzzle where you collect the information and try to build a kind of scenario where things could have gone wrong. So that is very important. So my sincere request to whoever is connected in this is to have this done every time, because unless this is done, we will not be reaching to the correct root cause of failure analysis, or we'll just it's kind of a eyewash, or we will not be doing justice to the job. So these are the three steps, and then the third step. I forgot to talk about the third step. First is FIR, second is taking all the observations in the field, and third says when the parts received at the analysis for analysis. Touching the part will be the last step that one needs to do. First, you have to capture all the visual observations in the part, then do all the entities that are possible, and then actually go for any kind of destructive test that has been designed. So it is all sequence, it has to follow sequence. Otherwise, we we can miss a lot of important things, and later on the bad part is, or the ironic part is, we cannot go back and have those observations once we lose that critical time uh, in doing those observations. So this is the SOP. Actually, we can talk a lot about it, but because of the time restriction, I'm just concluding on the SOP part here. So right, are you ready? Is everybody ready for the quiz? So I'll just open it for the quiz now. So maybe what we can do is, people can simply read and chat, say, or and then we can just solve it once everybody is done. So you can take couple of minutes, and in the chat box you can say one true or false, two true or false, three true or false, and also the second part is just you have to indicate the A, B, C, D in the chat box. Let us see what people can do. We just spend couple of minutes and then we'll solve this. Is that okay, Dr. Singh? Hello?
Yeah, it's okay. It's
Yeah.
okay.
Yeah.
Yeah. So people will dwell on it for a minute and then we will solve. Yeah.
Yeah. Correct.
Yeah. People have started posting their answers.
But how to see, because I'm not able to see that.
In the chat box, they are doing it. So below you will see the chat. Okay. What are the most this thing? One is yeah, they have, some people have talked about one as true and say some have said one is false.
Okay.
Second is true for
So,
many. Yeah.
Yeah.
He can conduct online.
Yeah.
Okay. Okay, so is everybody done with their choices, or tried at least the 10 questions?
Yeah, they are on the true and false of fifth.
Okay,
Yes.
okay.
So now still
We'll
the
wait
filling
for a
the
minute more. Yeah.
yeah, fill in the blanks. Yeah.
Okay. Okay. Okay.
So grain fiber structure. Yeah, great Bhuskar. Yeah.
Yeah, I think a lot of people are.
Yeah. A lot of people are posting now. Good,
Yeah.
Rajesh. Good, Rajkiran. Yeah.
Yes. Actually, when I do it in a live session, it is very interesting because we give them the sheets, and they give their choices, and then we solve it for the whole group, and then we later rank them how they are scored.
So I think most yeah. So I think we can go ahead from true or false. Yeah.
Correct. Correct.
Yeah. So ductile
So if you can
fracture.
see here,
Yeah.
the first is, yeah. So just for the benefit of the entire audience, ductile fracture is sudden and it exhibits no plastic deformation, which is false. As we saw that it has a plastic deformation, considerable
Yeah.
plastic deformation before failure.
True.
Yeah. Just a minute. I'm not able to see it properly.
Brittle fracture.
Yeah, brittle fracture has bright and shiny appearance, which is true. And ductile has gray and fibrous appearance. So this is true. Second one is true. When stress below endurance limit, the component can enjoy infinite life, which is true, because it will have a very good durability if the stress is not exceeding endurance limit. Then chalk on blackboard is an example of abrasive wear, which is false. It is adhesive wear because I explained you. adhesion happens between the conducting surfaces. And at sub-zero temperatures, metals become more ductile. This is again false. So first is false, second true, third is true, and then rest two are false. So you can decide like whosoever has got it right. And then in the MCQ, gray and fibrous fracture appearance is typical of ductile, that is B. Then brittle fracture mode is fast, C,
Fast.
fast mode. Yeah, fatigue occurs in 3 stages, C again. So B, C, C. And where due to aspirative collisions between sliding surface is adhesive, which is A, where, and with this scanning electron microscope coupled with EDS, that is C, we can characterize the defect and also indicate the source of the cell. So this is a kind of knowledge check that is done. So I think congratulations to all the audience who have got it right, and the people who haven't got it right, maybe the time may not be sufficient for them to really read.
सर लास्ट क्वेश्चन का आंसर क्या है?
Last is scanning electron microscope and EDS.
EDS. Okay, thank you.
Yeah. So thank you very much all for having participated in the quiz. Now I'll take a couple of minutes just to conclude my presentation here. So as I mentioned, I have a slide made on takeaway. I'll just So this is a takeaway that I want all of you to have from this presentation is, I talked about in the first slide, leading thought, that the experts solve problems and the geniuses prevent them. So how to get to that level, how to get to that expertise and how to get to that genius level is summarized here. So so that's why. So any expert or genius, they are called successful people. So how to become successful is nothing but gaining expertise in the domain. That's depth of experience. So the domain of failure analysis, how much deep one can go, as I described in SOP. Hello. Is there anything?
Continue, sir.
Can I continue?
Yeah, please.
Screen is not visible.
No, screen is perfectly visible. I think maybe your this sometimes this internet plays missing.
Yeah. So shall I share it again?
Yeah, you may, but it is already there on the screen. Yeah.
Okay.
Maybe
Hello.
Yeah.
not visible actually.
Hello.
Yeah.
Sir, can I have some addition, or just would like to add up my thoughts?
Yeah.
Just
Actually,
a
let
moment.
me just finish this.
Let him complete first. Yeah.
Sure, sir. Sure.
Yeah. Let me just finish this portion, which I thought is very important. So, is everybody able to see this slide, or do I need to share it again?
Yes.
I am not
Yes,
able
yes.
to see. I don't know that pulse.
But if majority is able to see, otherwise I'll share it again. Like screen share option.
It is
So
visible.
it is visible. You go ahead.
Okay.
Yeah, you please go ahead. Please go ahead.
Okay. So I was talking how to gain that expertise and go to that genius level. Is nothing like we need to have a depth of experience, which is technical depth. How deep we can go in the domain, that will determine whether we gain that expertise or not. And having that expertise, nothing but becoming successful in what we do differently in the domain. So when we say failure analysis, how many different cases we handle, one handles, is the width of experience. So to become expert and in the journey of becoming genius, these two are very important. Developing technical depth and also the width of experience. So for that, we need to be continuously practicing the tools that we know in failure analysis. So that will keep on like sharpening the edge and gaining knowledge. So that practice will make us, every time when we do, we'll be precise or we'll be perfect. So that is the journey to, gain deep knowledge, which is expertise. And then it it should so happen that it becomes our unconscious competence. So that becomes our DNA. So when it becomes our DNA, then that journey towards genius is accomplished. Again, this cycle repeats because we have to stay at that level. So this cycle will never end. So we have to continuously, work through this cycle to, remain competent in the field. So that is how it is summarized here. Series of successes and occasional failures brings in expertise, and repetitive demonstration of expertise makes one genius. I think with that, I end my today's presentation. Thank you all for your patient listening and, attentive listening. And I really appreciate you for, your active participation in this. Now I'll open it for Q&A. Thank you.
Yeah, just a moment. What we will do is there are a lot of questions in our chat box. So we'll have to
Okay.
first take them because that is in the order of the questions which
Okay.
people have
Okay.
posed. Yeah. So first of all, thank you very much, Mahesh, for doing it excellently. A lot of people have appreciated it. Also appreciate that your some friends like I think Daniel from Mexico who had joined, and also
Oh,
Clarissa
good.
from wherever in the world, I don't know, but she has also joined, and
Mhm.
there were a lot of diversity in this group today. I could see. So nice that a lot of people have joined this. Today we had a whooping 187th as a participation, and
Yeah.
there are a few questions in the chat box, so we'll just go through it quickly. Yeah.
Yeah. How do I see that? Because I'm not able to see that. How do I see that?
On the chat, you have to go down at the chat.
Yeah. Shall I stop sharing this?
Yeah, you can stop or you can keep it, no issues.
Okay.
Yeah,
Because I'm not able to see that. Okay.
yeah,
Now
yeah,
I can see. Yeah.
yeah. So what I'll just read out a few questions to you,
Sure.
who have been which have been posed, and then you can answer them. Okay,
Okay.
there is one question as regards the grinding burn.
Hmm.
Yeah,
Yeah.
how to identify the grinding burn and work on it. So that is the question from I think Bondiji. So please answer that, then we'll start. Yeah.
Yeah. So it's a very good question. Actually, I have handled a lot of grinding burn failures in my career. So basically, as you rightly said, identifying grinding burn, there is a, etching process that is involved, and uh, through that etching process with, say, first with HNO3, then with HCl, we can see bands or the, discoloration of the surface. So if you see very dark areas on the surface, that indicates that there is a grinding burn present, and the hardness of that area will be lower than the rest of the spot area. And if you see a light or bright spots in the grinding burn test, then those indicate the rehardening. So when there is a grinding abuse that happens for a part, there are three things that can happen. First, it can crack. There can be grinding cracks. Then if the grinding is less severe, then it can have a rehardening effect on the part. So the part, as I indicated in the burn test, you see lighter areas or the shiny areas in the on the edge surface. And if further toning down the severity of grinding, it will burn the sample. So there will be dark spots on the part. So grinding burns will have lower hardness, and then thereby they will fail because of that. And grinding rehardening will definitely be a adhesive due to effect of adhesive grinding, and it will cause kind of fatigue failure for them. So all these three things will essentially cause a fatigue failure of the part in application.
Yeah. So another question is how to identify crack initiation point. So if you could, because there are a lot of
Yeah.
questions, you'll
So
have to be.
as I told, yeah. So is there anything that you want to add or shall I?
No. Just go ahead, sir. I just wanted to say that we have to, we'll have to quickly answers them,
Yeah, yeah,
answers
sure.
this, yeah, and it will not
Yeah,
be possible for answering all for the paucity of time.
yeah, correct.
So maybe,
Maybe
yeah,
we can
and the
take three
topic
more
is so
questions.
vast, yeah, topic is so
Yeah,
vast that
yeah, yeah.
converting it into 1 hour is
It's difficult. Yeah,
really it's a hats off to you.
yeah,
So, sir,
yeah.
go ahead.
Yeah.
Identifying crack initiation function.
Yeah, so basically crack origin or the fracture origin, I have told. There are two things that we need to do is to see that fracture under low power lens or stereoscope, and we can see if it is fatigue, then you can see where it has started from, whether it is surface initiation or subsurface initiation. Because if it is subsurface initiation, you can definitely see the fatigue striations or fatigue beach marks starting from a little below the surface. So, or if it is not surface, subsurface, it will start right from the surface. So, basically, stereo microscopic observations will give a lot of information about the initiation of failure.
Yeah. So somebody is also asking the similar question. So I think that has been answered. Now
Okay.
there is a question from Subhas Mahajan that how after knowing the component is failed due to fatigue, what is the solution for this?
Yeah, actually, see, as I told you, fatigue failure is the mode, but there can be different causes. The one I was talking about, I have seen several cancers failing due to grinding abuse or grinding burns or rehardening or crack. So, the moment you identify that this has failed due to this problem in the process, you have to go back to that process and correct that. Sometimes there may not be any part specific cause that can be noticed or analyzed. So it indicates that something has gone wrong with the application because of overstress or anything. So depending upon what we see on the part and what analysis we come up with, considering all the important data, so that determines the course of action, further course of action. So if the root cause pinpoints to the applicational issue, we need to concentrate or focus on application. Or if it pinpoints to material or process issues, we need to go back to the process and correct it.
So there is another question which is engine seizure. Will it lead will engine lead seizure is due to
Hmm.
abrasive wear?
No, no, it's
Can
not abrasive. So normally seizure happens due to hydraulic. So suppose if you are talking about an engine, diesel engine or any engine, it happens due to hydraulic lock. There is substantial, no, there is a hydraulic lock phenomena that seizes, and it breaks the crankshaft and all the powertrain components and all. So wear will not seize the engine, but definitely wear is a significant, it will lead to significant loss of function for the part. So part may not perform the intended function. And so it's a kind of extended kind of durability failure. So you will not get the desired life out of the component, but it will not lead to any kind of seizure.
Yeah, few of the people have talked about case studies would have been more interesting. Of course, for the
Yeah,
paucity of time, Seshadri sir we could not take it here. We only
yeah,
limited our scope to basics of failure analysis. Maybe in part two, if Mahesh agrees, we might take it in the some case studies in the part two. We'll see that later on
yeah.
maybe.
As I indicated, that is in my plan, and I'm going to
Yeah.
do
So we
that.
can do that
Yeah,
later on. Yeah, sure.
yeah.
So there is another question. Due to field contaminations, fracture origins reveals complex oxides and sulfides in ADS analysis. In such cases, how to differentiate corrosion fatigue with other fatigue? It's a good question, Sakti Velania.
Yeah. Yeah, definitely. As I told you, if there is a contamination or corrosive environment that is there in the field, then a very prominent feature you need to observe there is the fatigue will be always from surface because it is actually contaminating the surface and the fatigue initiation happening from surface. But if you talk about the material defect, failure due to material defect like inclusion, which also again oxides and all, so, but necessarily the fatigue initiation will be subsurface. It will never be from the surface. So these are the two quick things that will help you determine whether the oxides or whatever we are observing on the fracture first place, whether it is observed right at the surface or it is a little below the surface. If it is subsurface, definitely it is coming from the material inclusions, and if it is from field, it should come from the surface. You will not see any subsurface crack initiation.
So there is one interesting question: how to identify defects in metal injection molding and its failure analysis. He wants you to suggest some, for MIM parts, that is metal injection molding parts, are getting cracked after applying load. That's riveting operation he's talking about. So if you could suggest something.
Actually, I don't have much exposure on metal injection molding per se because I have not worked on that. But definitely it will be interesting to see. So if I would request that person concerned to get in touch with me.
Yeah, Mr. Shiva Banothu. Yeah, you can contact him directly.
Yeah,
I think
yeah.
his
In
phone
the
number
slide,
is,
you can see my
in the
details,
last, you can see at the
last
bottom, he has the phone number. Mr. Hiran Purohit has asked about during ADX, how to identify that alumina detected in inclusion, or is it from cutting wheel powder? It's a typical of.
Again, the same thing. I would say, like that can get see if it is from cutting thing, then actually it is not. It will be very loosely held, or it will not be very tightly held with the part. So that is the first thing that you can see. And second thing, that differentiates because the topography or the characteristic of the inclusion is different than the contamination that happens when cutting it. So it only the experience that will tell of looking at these different cases. It is a good question, but definitely the kind of features that we see on the contamination, we can definitely pinpoint whether it is from actual raw material or it is actually externally embedded.
Mr. Veera Raghavan Pandurangan, I think he's from Mahindra. Yes, at least one case to be discussed. We could try. But next time we'll definitely take your. There are a lot of people have talked about it, so we'll definitely next time we'll take it up. And because of all the pressures, I think Mahesh sir would oblige us in that. Yeah. So on behalf of him,
actually, to be very honest, 1 hour is also not sufficient for one case.
Absolutely.
So
Absolutely.
yeah, so that was so that's why I restricted this to cover the different types, and definitely there will be version 2 coming that will have more cases and detailed cases masking the confidential information.
Thanks, Anil. He has suggested something for Sudhakar. Burns are soft spots on grinding the ground surface and can be detected by chemical etching process. By application of sodium oxide and hydroxide and HCl on part surface. Yeah, correct. So that is one of the suggestions he has said. Yeah, so I think we have taken most of the questions. A lot of people have talked about nice and informative session, and of course the end was very great MCQs. So I would like to thank. Okay. So there is one this thing. Yeah, excellent lecture again. Yeah. So a lot of people have talked about excellent lectures and.
Thank you. I thank everyone for that.
Sir.
And appreciate the compliments and
Hello, sir. Sir, one question,
somebody
sir.
wanted to share one this thing, something in the
Yes, sir.
addition. Yeah, who's this?
Yes, sir. Myself, Sudhir here, sir.
Sudhir from?
Hello. Sir, Sudhir Kshirsagar here, sir.
From?
Hello. Sir, hello.
Yeah, you are from?
Sir, I'm from Subros, sir.
Subros, okay. Yeah.
Okay.
Yeah. Sir, I just would. Yeah, can I go ahead, sir? Hello.
Yeah. Sure.
Yes. Go ahead.
Sir. Yes, sir. First of all, thank you very much, sir. The lecture was very much informative and useful. Now, just coming back to the slide on the tools for the failure analysis, sir. During this, I also have seen that this respectively lubricant analysis and the particle count analysis. I mean, millipore and further particle count analysis also plays the major role in actually detecting the failures. So is that correct,
Yeah,
or
yeah,
can we
yeah,
add it?
correct.
Because
See, yeah, you can add it. Actually, I have just given snapshot of what is generally like in that. But as I told you, like whatever the allied information that we have, so in terms of that, that impacts the component's performance, as you rightly said, millipore, and so what does that indicate is there was a contamination, in the oil.
right.
So that also has a greater impact on the wear or the failure that we see. So that is definitely millipore information, and everything is very important in terms of getting, provided we get to see the connected or the related failure, like there's a heavy wear or kind of corrosive wear or erosive wear, or that those kinds of failure modes will definitely pinpoint to contamination. So when
Right,
you
sir.
normally
Right,
see
sir.
fatigue, then no, it is not that relevant when you see a fatigue.
Yeah, because I just would like to share, because what happens, like wear also happens mainly in the bearings because of the caking of the lubricant, I mean greases.
नहीं है ना बहुत है
Yeah,
Hello, hello,
yeah,
sir.
somebody was talking.
Hello. Yeah, can I continue, sir?
Yeah, yeah,
Yeah, please continue.
yeah,
Uh,
you're audible.
yeah, begin the propeller shaft and this trunnion. There are certain micro oscillations takes place, and the lubricant, oil gets flow out, and whatever is the inorganic remains, and that leads to the wear also. The phenomena is called the caking. So all such kind of
Yeah,
things can be added. So this is
yeah,
just
yeah.
an addition.
Correct. Yeah, so that is very pivotal. If you see any kind of wear, then definitely you need to look for contamination in the system,
Right.
internal as well as external. So that's very important.
Thank you, sir.
Yeah.
So
So
thank you very much to all of you, all the
yeah, and
participants from
Hello,
here
sir.
I see in the chat, that people are asking for some help and all that. So definitely you can get in touch with me on my cell. I have given in the presentation on my cell or my emails
Yeah.
for any of your queries.
Yeah,
Yeah.
yeah.
So, one
So
question, sir. Can you speak?
yeah, go ahead quickly.
Sir, is there any online course available for failure analysis related to that, sir?
We'll be doing it for 2 days online course. Shortly we will announce it. Would be in the month of July or August. Yeah. First 15 days of August. It could be that is the most probable.
Okay, thank you, sir. Okay, thank you.
Yeah. Yeah. You can contact our ASM India chapter for that.
Okay, sir. Sure. Thank you.
Yeah. Yeah, Hiren Purohit, I have noted your number. We'll discuss with
Okay, sir. Thank you, sir.
Thank you. Thank you, Santosh.
Okay, sir.
Thanks, sir, for doing excellently. And so it's time for everybody. I think it's 9. Yeah, we have crossed 9 today. So it was very interesting. Yeah, and very nice lecture and technical topic. Of course, for paucity of time, you could do that. You had to do it, compress it for within 1 hour. So definitely we will talk it out and make some good program of 2 days. Yeah,
Sure,
that's what
sure.
we.
Yeah.
Okay, thank you all participants. Good night from here. Yeah.
Good night,
ASM
good night,
India chapter.
everybody. I am ending the session. Thank you so much.
Yeah, thanks very much.